Cool. So, hello everyone. Russell. Today we're going to be talking about this paper called "Do as I Can, Not as I Say: Grounding Language in Robotic Affordances." So before we get into it, this paper explores using large language models like GPT-3, FLAN, and PaLM. Looks like someone joined. Did someone join? There we go. Cool. So this paper explores using large language models and exploiting its semantic understanding of the world in order to plan robotic movements. So let's get into a little bit behind the background of large language models. So as we all probably know, interacting with stuff like OpenAI's ChatGPT, GPT-3, FLAN, PaLM, large language models encode a lot of semantic knowledge about the world. What that means is they just have a lot of common sense knowledge. It's the first time that we kind of have a machine learning model that has this common sense embedded in it. They're typically trained on really large corpuses from the internet. They just scour different text from the internet, and they try to just gather knowledge from a whole host of different sources. So some problem with large language models is that they don't really observe the consequences of their generations. And this kind of gives a nonsensical and unsafe situation. So if you've ever interacted with a large language model, like let's say GPT Chat, which is a new one that came out recently, it's typically pretty good and it has some pretty good common sense, but the outputs, there's no consequences for it getting an output wrong. Most of these are trained in like a zero-shot fashion or a few-shot fashion where it's not supervised at all. So it can make mistakes really easily, and it can, it usually doesn't know that, and it can't really learn from that since no one is supervising it and telling it that it's making mistakes. So because it doesn't observe the consequences of what they give, we can get some nonsensical or unsafe prompts coming out of the large language model. And something else that's a problem with using large language models for robotics is that they're typically unable to provide context or contextual answers without users giving like really unreasonably long prompts. So for instance, if you ask a large language model, like, how do I mop up a spill? It might tell you, go to a store and buy a mop. It might also tell you, grab the broom handle and, start moving it in like a circular fashion around the spill. Obviously this all depends on what the spill actually is. It all depends on what the user has in store. And we can't just take the vanilla large language model output and use that as an instruction for a robot. So, like I said earlier, this paper kind of explores how we can use prompts in large language models, so natural language prompts, and large language models to plan robots. So an example here that I have that was given in the paper is, I spilled my Coke on the table. Can you throw it away and bring me something to clean up? So natural language is a really convenient medium to interact with things, right? We can express what we want very well in natural language because we're humans. That's just how we normally interact with things. And there's a few key challenges here to actually getting robots to understand these prompts and give good instructions that a robot can understand. So first of all this knowledge that a large language model might output. So let's give that last prompt. How do I mop up a spill? Go to the store and buy a mop. Go to the store and buy a mop. That's something that's locked behind natural language, right? A robot can't understand what that means. We have to find some sort of way to instruct the robot given the prompt that the language model outputs. Also, large language models lack the context of the state that the robot's given in, right? It's only given some sort of text input. It doesn't have some sort of image input to help it. It doesn't have any knowledge of like what the robot's grasping, what the robot can even do. It just lacks the context to give a really good response. And also the answers to the prompts, I already went over that, but the answers to the prompts can't really control the robot on its own, right? We need some sort of way to expand that. So the big question, can we use prompts and LLMs to plan robots? We can. And before I go into the details, I'm just going to show you guys a demo video to spike your interest. I think it's really cool. So here's a video given by the paper authors. where they give the same exact prompt. I said, I spilled my Coke on the table. Could you throw can you throw it away and bring me something to help it clean? So here's this robot understanding a very long prompt. It's able to dissect that and output a step-by-step command to do what the user asked. And we'll go over how they actually accomplished this before, but it's really impressive how it breaks down the original task that obviously takes multiple steps to complete. Cool. Let's go to the next slide. Cool, so how did they accomplish this? So the method behind this, and I'm going to go into this a little bit later. First, we give the robot a set of low-level instructions and skills that it can perform. So these are skills that are associated with like some sort of prompt in natural language. So for instance, opening a door could be a low-level skill. Opening or like placing down what's in its clamp can be a low-level skill. Next, we do some sort of prompt engineering, which is restructuring the prompt that we give the large language model, and we prompt it in such a way to act like the robot is giving a response of how we can string together lower level skills in like a sequential order. Next, we find what large language model, what skill is relevant given the previous steps using the large language model. And then we create an affordance function which ranks the feasibility of actually accomplishing these tasks. And again, I'm going to go over this in the next slides. And then we iteratively just keep asking the LLM to fill in the blanks. What's the next step? What's the next step? What's the next step? Until it comes up with all the steps to do the given task. So here's that method kind of drawn out. So on the left side here, we see the original prompt, which is how would you put an apple on the table? They do some sort of prompt engineering, which is they make the robot reply with I would, and then they start a bulleted list with 1. Here are all the actions that the robot could take, which is finding an apple, finding a Coke, etc. It ranks what is the most relevant prompt given the steps that it has already taken and the input prompts. And we also somehow score all of these actions with what are the feasibility of completing these actions in this given state. And then we just keep repeating that. Cool, so let's go into how they actually did this. So the low-level skills, this was done before the paper was written. This was actually done by a Google sub-company called Everyday Robots, which is under X. Which is one of their research labs. So they already had 511 diverse skills for manipulation and navigation in a kitchen environment. And they do it on this mobile manipulator here, which we saw in the video. So every single skill has a text description, and that's really important because the large language model can select those text descriptions, and once it selects a text description, it can perform the task that was already trained on that robot. Next step, the prompt engineering, which is just the art of getting LLMs to say what you want. So here, like I said earlier, but before they prompt the LLM to give a response, they fill in a part of its answer with I would, and then they start a bulleted list. That way the LLM is more inclined to give like a sequential instruction. Cool. Next step is determining the task relevance using the LLM. So the large language model can rank which responses are most relevant given the original prompt and the task that it has already done. Cool. And this is like the groundbreaking thing here is grounding the responses using some sort of affordance function. So using some sort of external function that measures the feasibility of completing a task, they are able to multiply that score with the score that the LLM gives them and select the highest combined score. And and do that task rather than just doing what the LLM would say. And the reason why this is so important is because this gives the LLM some sort of idea of what the state the robot's in, right? So for instance, if there's no apple in the kitchen, well, it can't do anything, right? But the large language model has absolutely no way to know that without this value function helping it in some way. And then the last step is just iterating over this process until you hit a done instruction. So that's not pictured here, but done is one of the instructions where it just ends the task. And it just keeps doing this until it finishes the task. So how does it actually do? So out of all the tasks that they tried in real life, they did 101 different tasks. It was able to plan successfully 84% of the tasks and execute 74% of the tasks. So the execution isn't really what's important here. It's more of the planning, because that's what the major breakthrough was in this paper, is actually using the LLM's knowledge combined with the state knowledge to plan some sort of trajectory for a long-term temporal prompt. So you can see on the left side here, mock kitchen is the one that's important. We get 84%. Versus no affordance, which got a 67%. So that means that affordance, which is where we rank the actions based on how feasible they are, based on the state, that boosts the performance by about 10%. I think it's the same video. Yeah. Cool. Yeah, and something else that's really cool here is they also get some pretty good results here, 74%, using a slightly different method that I'm not going to go into, but they use some sort of like mapping of the large language model with the actions. I think they take some sort of intermediate state in the model, and then they use that to like extract semantics. I don't understand it too well. It's some sort of like complicated NLP thing, but it's pretty cool if you want to look into it. But baseline 67% performance, and we get about a 10% boost. We get a 10% boost using the fancy method. We get an even bigger boost using the baseline method, which is the no VF. Cool. So something else that was really cool from the results is that performance improves just by improving the underlying language model. So this kind of suggests that that this whole system is actually using the semantics that the language model has embedded inside of it. And the better that the language models get at understanding the world around us, the better the performance is going to be at creating long-term trajectories for tasks like these. So on the left side here, we have PaLM, which is a new model released by Google, and FLAN, which is an older model. It has about 5 times more parameters. You see the performance increases by 14% just by swapping the LLM that was used. Cool. So into some discussion. The authors also mentioned that an inner monologue might help performance in long temporal tasks. So what this kind of means is they're going to allow the robot to talk to itself inside of its head while it's doing a task, and that is going to help this execution part. Because let's say in the middle of it doing a task, it notices like, if I'm supposed to pick up an apple, I just dropped the apple, and it tells itself, I dropped the apple, this is bad. They can early terminate training, they can early terminate that task and better replan. Yeah, and that's a new paper that they released really recently. So if you guys are interested, check that out. Maybe I could present that sometime. And that inner monologue also allows the model to reason about its environment mid-task rather than just the beginning of the task when we use that affordance function. So some other things that they noted from the discussion is that LLMs obviously have the bias of its training. So this is good and bad. It's bad because it tries to make assumptions about the world based on what it sees from scraping the internet. But it's also good because this means that this whole system is multilingual despite not being designed to be multilingual, just because these large language models have such a good understanding of the world, and that they're able to be compatible with many languages. And they also said that the system is bottlenecked by the lower level skills. That's something to be improved on in the future, because we don't really have another way to translate pure text output to some sort of robot action. It has to be these, well, they call it lower level skills, but these are like really high level commands. Cool. So something else that came out of this is they have an open source data set and simulation. So you can just download their Colab notebook and run this in Google Colab. And this is a version of SayCan that just works on a tabletop environment rather than that robot that you saw earlier. Cool. And here I have one more video. This is the longest chain that they were able to get from this robot. So I believe this was 16 subtasks. So you can see here on the right, this is kind of like the prompt engineering, where they just keep bulleting every time something new comes up. Yeah, these robots are also really cool. I don't know of any other company that has this, so.
I really like how they're able to enact an exact response when something new happens.
Mm-hmm. Yeah, it's pretty cool. And these robots are designed by Everyday Robots, which is a company that's designed to. I think their motto is make robotics boring, so just integrate it in human lives, which is why they have 511 skills to begin with, because they have a really advanced simulation and some other stuff. It's a pretty cool company. Cool. And then once it successfully completes everything, it has that last done task. If you're late, I'm gonna yell at you, single you out. I have one more video, which is the inner monologue. So I didn't read this paper fully, but I did read it a little bit. So we can talk about this afterwards. But you can see on the bottom, the robot thought, how in the middle of a task, it'll start to reason about what it sees. And I think this one also uses image input as well. I could be wrong about that. Or maybe it's just at the beginning. Like I said, I haven't read the full paper yet. But yeah, in this example, this does something that the paper that we just discussed can't, which is reason about stuff like fruit-colored drink or fruit-flavored drinks. The original implementation is really bad at stuff that has ambiguity, and having an inner monologue like this helps improve that just a little bit. Cool. So it didn't go too deep into any technical implementation and stuff like that. So I'll take any questions and patch any holes if you guys want to know anything else. Watch the chat here.
I noticed some of the values were negative when it came to making, the decision.
Yeah.
Why they're negative?
So I think that's just the way that the LLM scores it.
Right.
So as far as I know, I'm pretty sure it goes word by word, and they sum up the probability of that entire prompt being appropriate for the given prompt and the actions already taken. So I think it's just a sum of negative values, and then when you multiply it by a number, you just take the highest value afterwards. But it doesn't matter if it's a negative or positive. Oh, actually it does, because it's being multiplied. Because it's being multiplied by a float, my bad. Yeah. I guess this makes this makes it a little bit easier if one number is negative and one number is positive, because you could just take the max. Yeah. So otherwise the value function would have to be like out of 1 to 100 or something like that. And they tried to scale all the values from 0 to 1. And yeah, the affordance function is also pretty cool, because they had to, so they didn't like train a network to do this or anything. They just do some like really basic values that gave the whole system a little bit of awareness about the environment around them. So for instance, any navigation task is just the total distance traversed. Yeah, and I think like the done function was always 0.1, so that if there's no other better option, it would just choose done. Yeah. So they did some really cool engineering behind the task affordance as well. Go back here. I want to call on one of you. I feel like a teacher. Nick, you want to say hi?
What's that? I was gonna actually ask about like, do you see this being able to be done on not pre-trained tasks, like having it be able to come up with the task itself and be able to discern like basic actions and ways to complete a task through basic actions that it knows?
Yeah. Completed tasks through basic.
Like
actions.
coming up with its own basic.
Oh, coming up with its own lower level like control.
Yeah.
Yeah. So I did see some stuff like that. Just through reading stuff on my own, where they essentially make like a programming language that the large language model controls. That's in a different paper, but yeah, that is a thing, and it's not as complex as this, where we navigate in the real world. We have to like open up drawers, which is really hard, by the way, like grasp different objects and stuff like that. It was more like it was on a tabletop, and you had to like rearrange different colored blocks and shapes in different ways, and it was able to write code to like grasp stuff in a very, in a lower level way than this. So yeah, it pretty much was like programming itself. Try to see if I could find it. I think it was this one. Yeah, it was this one. Yep, so let's take arrange blocks in a square around the middle. So this is the code that it generates to do that. So like this is really impressive actually. Like it can even make a square. Like it knows how to make functions and stuff. This isn't its own weird like programming language. This is Python. It's pretty cool.
Is this more focused on creating code rather than robotics? Because it feels like those are two different.
Let me show you the whole video.
They're combining like two different things here.
No. Let me show you the whole video.
Horizontal line.
Come on now.
Arrange the blocks in a square around the middle.
So it gives a prompt like through language. So a user just says arrange the blocks in a square around the middle, and it thinks about that, and the large language model is able to create this code and then executes it. This isn't actually Python, my bad, but.
Okay, arranging the blocks in a square around the middle.
It's a little slow, but you see like it actually performs the manipulation task. It's a little slow, but let's see. Yeah, you get the idea. Maybe a more complicated one. Put the blocks on different corners clockwise, starting at the top right corner. Like that's a pretty complex prompt that this person gives it. And it's able to generate code to do that. Let's see. think even 2 times speed is pretty slow. But it's pretty impressive at all that it can do this. So does that answer your question, Nick?
Yeah, I was just kind of pointing out that this seems more just like language model to code rather than like language model to robotics. You know what I mean? I mean, it's
Well,
what the code's needed for the robots, but it just seems like it's more just turning like statements into code, and then it just happens to be running on a robot. Does that make sense?
I kind of see what you mean, but it is like manipulating what it sees. So it sees it in this case, I think it also gets the image input. So it's able to manipulate its environment by spitting out valid code.
Oh, okay. I thought it was just purely based off of what was being said to it.
No. Like it sees what is on the table and it spits out valid code to manipulate its environment.
All right, that's better.
Yeah.
Okay,
Yeah.
that
So
makes
this
sense.
is pretty cool if you want to check it out. I'll drop this in the server. You have any more questions?
I got nothing else.
Gotcha. Yeah, sorry, Janan, you missed the first. I mean, I think you missed all of it, but I'll post a recording after this.
Yeah, I will be sure to listen. I came in much later than I expected.
You're all good. It was a pretty short presentation. That was like, what, 20 minutes? So. And then Saad, do you have anything? I think Saad's gone. All good. Cool, so.
I think he said his mic was broke, so if he says anything,
Oh, his
we
mic
can
is
chat.
broken? I see. No worries. Cool. So I'm going to stop recording then. The wrong one.